Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to celebrate the 50th anniversary of the Star Trek series. That's right, it's hard to believe, but it's been 50 years since the Star Trek Enterprise blazed the way for science as well as science fiction. And with us today to talk about the 50th anniversary is the author of Star Trek, the official guide to the universe, Andrew Fazekas, who is a commentator with the Canadian Space Agency and Canada's Weather Network channel. Author of the book Star Trek, the official guide to the universe, with a foreword from William Shatner and over 400 full-color illustrations in that book. You know, we have to look at the relationship between science and science fiction. After all, the greatest astronomer of the 20th century was Edwin Hubble of the Hubble Space Telescope fame. And he was destined to become a country lawyer, but as a child, he remembered reading Jules Verne. And because of his romance with Jules Verne and all the books talking about the exploration of the oceans and the universe, Edwin Hubble dropped his job being a country lawyer, went to the University of Chicago, got a Ph.D. in physics and astronomy, and went on to discover the expanding universe, which eventually led to the Big Bang Theory. Not to mention the fact that Edgar Rice Burroughs, author of the Tarzan series, wrote another series called John Carter of Mars. A young boy by the name of Carl Sagan read that book, and he said, wow, he wanted to go to Mars. He wanted to go to the Red Planet and chase after Princess Dejah Thoris, just like John Carter of Mars. And Carl Sagan went on to become an astronomer. So many times, children inspired by science fiction go on to become professional scientists. Many scientists at NASA, for example, can swear that it was watching Star Trek on TV in the 60s and 70s that launched their career in the sciences. Now, for me, it was a little bit different. I remember watching Flash Gordon every Saturday morning, and for me, hey, I was hooked. By that time, I already knew I wanted to become a physicist. I was reading everything I could about Einstein and the unified field theory. But then watching Flash Gordon explore the stars and the heavens every Saturday morning, I said to myself, wow, starships, cities in the sky, what's not to love? Even George Lucas got his inspiration for Star Wars by watching Flash Gordon.
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to dedicate it to Star Trek. That's right, to Star Trek. Did you know that it's the 50th anniversary? And there's a book called Star Trek, the official guide to the universe. So today we're going to talk about the Star Trek universe, not the universe of actors and actresses and production studios, but the universe, well, the real universe, the universe of stars, planets, and galaxies. And with us today to talk about Star Trek, the official guide to the universe, is the author, Andrew Fazekas. He's also known by his popular nickname, the Night Sky Guy. We should say that he's a science writer, broadcaster, and he's a regular contributor to National Geographic News. He's a correspondent with the Canadian Weather Network channel and a consultant to the Canadian Space Agency. So, Andrew, glad you could be on Science Fantastic.
It's great to be here. Thanks for the invite.
Okay, first question that we always ask our guests is, how did you as a youth first get interested in science?
Wow, you know, I really have to give props to my dad on that one because from a very young age, he introduced me to all kinds of sciences and nature. My dad is a medical doctor and also a cancer researcher. And so I was very fortunate to be able to go into his lab, his biochemistry lab, and see the things that he had, all the wonderful instruments like scintillation counters and microscopes and all kinds of neat things that he had in his laboratory. So that really sparked an interest in sciences as well. But also, he loved going out camping. And so my dad and I, we would go out camping and fishing a lot. Growing up in Canada, we've got wonderful nature here, and we would go out to the backwoods and go on to very remote lakes in Canada and go fishing in the summertime, and sitting around the campfire, looking up at the stars. My dad would basically teach me the constellations and the mythology associated with it, and point out really interesting things. And this interest in astronomy just kept going and going throughout grade school, and my dad sort of finally gave in. I think he was watching to see how interested I was in astronomy, and just wanted to make sure that it was going to stick. And then at the age of 12, he bought a Celestron 8-inch Schmidt-Cassegrain it's quite a nifty instrument with a drive, a mechanical drive to follow the stars, and that's it. I was really hooked, and I started doing like little projects on variable stars and looking at comets and of course the planets. And back then, and this was in the early 80s, there was no computers, no apps on iPads to figure out where the planets would be. I would actually bring out my calculator and calculate out where the planets would be, where the moons are going to be visible. It was just a fantastic time that really opened my mind to the universe.
And I should also point out that I'm a physicist, not an astronomer, and I took my telescope out, and I didn't know where the hell I was looking at. I didn't know where the stars were, where the planets were, and I kind of gave up. Now it's all computerized, right? You just point the telescope in a certain direction, and off you go. But I said to myself, I'd rather be a physicist than an astronomer. But I guess you can do both.
That's right. Now we've got the go-to telescopes. You just punch in the name of the object, and off the telescope whizzes and just beeps when it gets there. So it takes the challenge, I think, though, out of the search, the quest to actually find it. The hunt. The hunt is really, I think, part of the fun. So when I, as an astronomy educator now today, I try to encourage people to make sure you learn the sky, learn your way around all those wonderful constellations, because it'll make it that much easier to, when you take that telescope out, to find your way.
Now let's leave the universe as it actually is and talk about the Star Trek universe. It is the 50th anniversary of Star Trek, hard to believe, and there's a book, The Star Trek Official Guide to the Universe, by Andrew Fazekas, who's with us here today. So what steered you in the direction of the Star Trek universe?
Well, I think that goes back to my childhood, because, as I said before, I was, introduced to astronomy at a very young age, and that really is in connection directly with Star Trek, because at the same time, one of these rituals that my father and I did was watching Star Trek episodes. And this was back in the early 70s. So I guess it must have been one of the first times they were rerunning the original series with William Shatner and Leonard Nimoy from the 1960s. So that was the first reruns, and I was watching them on Sunday mornings, and it was something that we just did all the time. I would scoot into bed with my dad and watch it in the morning, Sunday mornings, and I would barrage my dad with questions on and on about what's this going, what I'm seeing on Star Trek, what are those planets and stars, and how is this possible, how are they getting where they get. And I think I just beat my dad down, and that's when he got a telescope. And so that connection between astronomy and Star Trek goes back back to grade school. But then flash forward, as a young adult, I became a very dedicated amateur astronomer, and I loved doing astronomy outreach, and that involved, with my local astronomy club, I would go out to do public events and bring out my telescope to show people the stars. the heavens. And what I noticed very quickly is that to really engage the general public, if I would invoke Star Trek analogies and showcase objects that I became familiar with in my in Star Trek, in my viewing of that series, and then just sort of pick out a few objects that have real-life counterparts and just talk about it in terms of Star Trek to the people, that really engaged them, made them very fascinated. And so I began to put together a list of objects that was visible within the Star Trek universe that had real-life counterparts to them that I would be able to show at the telescope. And that really became, I feel, the seed, I guess, of the basic seed of the book.
I should also confess that when I was a child, I used to watch Flash Gordon on Saturday mornings. Of course, there was absolutely no science whatsoever in Flash Gordon. It was all fantasy. But again, it sets you off on a journey. George Lucas also says that it was Flash Gordon that set him off to create the Star Wars series. So now, let me ask you a question about Star Trek. How did you get involved with the Star Trek universe? Have you met the cast? Have you met William Shatner? And what about Gene Roddenberry?
Well, yeah, I've the only cast member that I've actually met personally is George Takei, who plays, of course, Sulu in the original series and throughout some of the movies in the 1980s. And I had the good fortune of meeting him a number of years ago when he came out with his own biography, and he went on a book tour. And he came to Montreal, and I said, my goodness, I got to go out and see him. And I had the good fortune of talking with him a little bit. And it just really was very inspirational to having actually met somebody. I think I was really starstruck, if you can say that, having met him. And with this book project now, I'm still to meet. I mean, my dream is to meet the cast, and I will be going to Star Trek conventions in New York, the Mission New York, on September 3rd and 4th, where there's going to be many of the cast members there from all the different series, including William Shatner himself. And so I'm hoping that we'll be able to meet in person. My dream is really to make sure I have my book, my personal copy, signed by as many of the cast members as I can. But William Shatner, I included him in the foreword. When I finally found a home for the book with National Geographic, I told the folks there that I had to have Captain Kirk himself sort of set the scene for the book. I really wanted that. That was something extremely important for me. And because he's such a larger-than-life character, Captain Kirk, I mean, he's really a cosmic swashbuckler of sorts. And to me, he's kind of like an Errol Flynn type of character almost. And he really embodies the spirit of adventure. And so this is on the cosmic scale. And he personally is interested in science fiction and science as well. So we were very fortunate to get him. I said to his personal assistant to, I tell him that I'm from Montreal. I tell him I'm a fellow Montrealer, just like William Shatner is. I was born in Montreal, and we went to the same university, McGill University, and I guess that those appeals were successful because I landed him for the foreword.
Okay, now let's talk about the program itself. What was your favorite episode, an episode that sticks in your memory? What was one of the favorite episodes of Star Trek that you liked?
Wow, that's a big question of which ones are my favorite. But I think the City on the Edge of Forever really stands out, and I'm not the only one. I've talked to other fans too. It's from the original series, third season, and it's an episode that involves so many levels. It's just a beautifully done, beautifully written script.
It's a time travel episode, right?
I'm sorry?
It's a time travel episode, right?
That's right, exactly. It's a time travel episode, very well known because it has a guest starring
Joan Collins, right?
That's right, Joan Collins. That's right, a famous actress, and she plays Edith Keeler, who's running this mission for folks, and in pre-World War II. In the United States, and she falls in love with Captain Kirk, and it's a tragic romance because she does get killed, and of course Captain Kirk has to wrestle with this idea of can he save her, or should he save her, or just let her die, and of course logic prevails, and he has to let her die because if he does save her, then that will change the course of history. And so within that episode as well, there's this nice scene where they're out on a date and walking on the street, and Captain Kirk looks to the heavens and points out to Edith Keeler a star in the sky. And that star is actually one of the stars in the belt of the constellation Orion. It's a real star. And I have this memory of that as a childhood memory of watching that, and my father actually taking me outside and showing me that very same star in the belt of Orion. So there's this really deep connection that I have with that particular episode.
Well, some science buff asked the question, what lies on the other side of a wormhole? Well, we know the answer. It's Joan Collins. Yes, she's on the other side of the wormhole, and that's how they go back into the past. Now let's talk about some of the science or lack of science in Star Trek. Whenever the Enterprise goes near a planet, the first thing Spock asks is it a Class M planet? That is it an Earth-like planet? Well, let's be real. Is there such a thing as a Class M planet, or is that just a fiction devised by Gene Roddenberry?
Yeah, I mean, that they had to come up with a hodgepodge mix of different kind of aspects of what a planet is to create what is an M-class planet. There is
Andrew, we have to take a short commercial break, but after the break, we're going to continue a discussion of Star Trek, the official guide to the universe.
Don't feel bad. I didn't understand theoretical and dimensional metaphysics the first time either. But if you call and ask, Professor Kaku will get you there. You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's the 50th anniversary of the Star Trek series. And to commemorate that, there is a new book, Star Trek, the official guide to the universe, which mixes science and science fiction. With us here today to talk about the book is Andrew Fazekas. He is commonly known as the Night Sky Guy, a science writer with National Geographic News. He's also with Canada's Weather Network and also a consultant for the Canadian Space Agency. Where we last left off, we were talking now about the science behind Star Trek. In Star Trek, they talk about Class M planets, which I imagine means Earth-like planets, but actually there's no such thing as Class M planets. However, the Kepler satellite orbiting in outer space has confirmed the existence of over 1,000. So, Andrew, the question is, did Star Trek get it right in describing some of these planets, given the fact that we now have an encyclopedia of over 1,000 planets orbiting other stars in the night sky?
They've gone into their own type of fictional planetary classification, that's for sure. And M-class, their M-class of planets is probably the most similar to what we're looking for, this Earth 2.0. Planets that have Earth-like qualities, specifically, in the habitable zone around a star where water can exist in liquid form. This is something, if you look at the fictional classification that they have, they were looking for planets, M-class planets, would be ones that have an atmosphere that contains large percentages of nitrogen and oxygen. The surface would be abundant with water. Their cores would be made with things like nickel and iron, things that are pretty much analogous to what we're looking at in Earth terms. And Gene Roddenberry and his science consultants, which, by the way, were always used throughout all the different series, television series and movies, they came up with this fictional canon. But you have to remember, back 50 years ago, looking for actually detecting planets was out of the realm of possibility at the time. The scientists 50 years ago believed that planets would not be able to be detected because the light, the reflected light, would be way too feeble compared to their host stars. So we've gone really light years ahead in many respects of now having this encyclopedia galactica of all these planets that we're detecting through, of course, mostly indirect methods. And what's interesting is, I have to say, is that within the Star Trek universe, when they were trying to characterize M-class planets, many times the Starship teams would have to send probes or teams down to the surface to really analyze it, to really determine exactly what class of planets. But their classification was very intricate, and our real-life classification planets are nowhere near there yet because we just don't have enough information of being able to class them to, different. They had over almost a dozen different classifications in the fictional years, and we're nowhere near that with our knowledge yet. But that's yet.
Now, for fans of Star Wars fans knows that there is a planet with two suns, and many astronomers, I still remember, many astronomers at that time said, bah, humbug, a solar system with two stars and planets going around two stars would be inherently unstable, and therefore Star Wars got it wrong. Well, who actually got it right or wrong? Don't we actually have evidence now of planets in outer space going around a double star system? So the astronomers were wrong, right?
So, this is where it's interesting, where, you have this confluence of fiction and science coming together, right? So, but the two have always been intertwined. When we're talking about good science fiction, it always involves elements of true science. So in Star Trek, when you were looking at both Star Wars and Star Trek, I'm always being asked this, who did get it right? And Star Trek tends to appeal to the inner geek, I think, in most people.
Okay, Andrew, we have to take yet another short commercial break.
Yes, Professor Kaku can help you with your homework. He can even help you with your kids' homework, but only if you ask.
You're listening to Science Fantastic with Professor Michio Kaku. Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, we have on the line with us Andrew Fazekas, author of the book Star Trek, The Official Guide to the Universe. Today, let's talk about the 50th anniversary of Star Trek. Star Trek, The Official Guide to the Universe is the book we're talking about today. The author is Andrew Fazekas. It has a foreword by William Shatner himself. It has over 400 full-color images, the science and science fiction. Well, you began to answer before the break, and that is between the Star Trek fans and the Star Wars fans. Well, who gets it more correctly in terms of the science?
I love both of them. Star Wars, to me, though, is more of science fantasy than fiction. So for me, and it speaks to my inner geek, Star Trek is more something where I can see the future in terms of our humanity and technology and the science of playing out. Now, there are some things there that, maybe not even in our future, like, for instance, the transporter system or the warp drive, things like that. However, there are so many other sciences, like the astronomy, the cosmic canvas that's in the background. Star Trek tends to get it right, but if I'm not saying Star Wars doesn't have it. Beyond the space opera that it is, you look at some of the worlds, some of those planets that are there as well. As we had mentioned, Tatooine being the prime example, there are things that now science is bearing out that can exist. And the producers, the makers of these films, are now trying to incorporate, real science discoveries to flesh out this canvas, this astronomical canvas that the space opera plays out on.
Okay, so let me ask you a question. Oh, we have to take a short commercial break. But after the break, I'll ask you a question. What was right and what was wrong in terms of Star Trek? Where did Gene Roddenberry get it right and where did he get it wrong?
You're listening to Science Fantastic with Professor Michio Kaku. Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about the 50th anniversary of the Star Trek series. And so before the break, we had a question. What did Gene Roddenberry get it right? Where did he get it right in the series Star Trek? And where did he get it wrong?
There's so many different things, right or wrong. Astronomically, maybe perhaps what they might have missed. I think one of the glaring ones was quasars. Quasar, stellar, these magnificent stellar objects that are basically these very strong active cores of galaxies that are literally hundreds of millions, if not billions of light years away. They were portrayed in the Star Trek universe, particularly in the original series back in the 60s, as objects within our own Milky Way galaxy, a sort of a stellar type of object, a star-like object. One particular episode is the Galileo 7 back in 1967, and you get to see what the object looks like, and it's nothing like what a quasar is, which is a much larger galaxy. It's an actual galaxy itself that's billions of light years away.
Yeah, but I remember back in the 60s, there was a legitimate debate among astronomers. There was a faction of astronomers who did think that quasars were very nearby, and that would explain their redshift, rather than being very, very far away. So, there was a debate back then.
There was a debate, exactly. There was a debate on what, and I think, Roddenberry and his team of writers had to make a decision of which way they were going to go. Now, of course, as time, it's kind of unfair because now with time, right, it's borne out that they are, extragalactic objects. But that was something that is interesting because if you look at the episodes today, they've been remastered. And the visual aspects of what the quasar looks like, they've changed it over time. So it was really interesting in the remastered version. It's worth looking at in the Galileo 7 episode. And then one of the ones that I really enjoy looking at is, again, in the original series, and it's been remastered to look absolutely amazing, but they got it right the first time, is All Our Yesterdays. And All Our Yesterdays in 1969 was really about this impending supernova explosion, this giant star that explodes. And they had to save people on this planet that's orbiting this impending supernova explosion. And it's just wonderfully, it depicts how the explosion occurs on screen. So that's one of the places that I think, astronomically speaking, they got it really right.
Well, one of my favorite episodes is in the Next Generation, where they pick up a time capsule from the past containing dead people from the 20th century who were frozen, hoping to be thawed out in the 23rd century or so when there's a cure for cancer. So they thaw out a banker. And he realizes, oh, my God, it's the 23rd century. I'm rich. My investments are worth a fortune. I'm rich. And then he talks to the crew of the Enterprise to track his investments. He must be a billionaire now. And they look at him and they say, what? What is money? You want something? You simply ask for it with the replicator. Which I thought was very seditious, right? In the future, if you want something, you simply ask for it.
Yeah, that's amazing. And you know what? That you mentioned that episode. It reminds me, of course, of the Wrath of Khan, right? Because if you think about the original, where they brought that character in the original series, there again, that was a group of humans that were in suspended animation from going back into 1990s in that script, and they had reanimated them. Of course, they were in a different time period completely, and that went on to be the showcase in Wrath of Khan in 1982 in the movie.
Now, what do you think was perhaps the most egregiously wrong thing on Star Trek? You mentioned that they got supernovae, they got some of the planets, they talked about the universe and its glory. Was there anything that really made you cringe?
Well, you know what? The concept of warp drive is something that I wish we would have, but we don't. And the transporter system of breaking ourselves down to molecules and then rebuilding it on the other side. It's obviously these are plot devices that make the story move ahead. And I can look at it on the side, but the inner science geek in me kind of cringes, going, I wish that we could have it. And then I know we're getting there in certain rudimentary ways with photons of light and applications for quantum computing and stuff, but actually being able to transport ourselves like that, and then, of course, the warp drive of going at those tremendous speeds, that, I think, is something that, it'd be interesting to see where we go in the future with those technologies.
Well, Star Trek takes place in the 23rd century, and before we have warp drives, we may be perhaps 1,000 years off. But it is conceivable that within 1,000 years, we may have enough energy to play with black holes and to warp space-time to the point where we have warp drive. But it's not for us. We're maybe 1,000 years behind the energy technology necessary to manipulate a warp engine. And teleportation, as you said, we can only teleport photons and atoms of cesium, rubidium, but not much more than that. So I think we're still a long ways from that.
And would you want to be teleported? That's the big question. If you had is that something that sounds like it would be a good idea?
Oh, like in what sense? I mean, who wouldn't mind being able to, teleport across long distances in an instant? But what are the drawbacks?
Well, I don't know. I mean, it's to me, it also speaks to the idea of if you have a soul, for instance, if you're being dematerialized like that, broken down into little bits of atoms and being rebuilt. I don't know. That sounds. I'm like Leonard McCoy, Bones. It kind of irks me. I don't know.
Okay. Well, unfortunately, that's it for Science Fantastic. Once again, you've been listening to Andrew Fazekas. The book is called Star Trek: The Official Guide to the Universe. So, Andrew, thank you so much for being on Science Fantastic.
My pleasure, and live long and prosper.
This is Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Without further ado, let's jump right into some of the listener phone calls that have been pouring in.
Hi, Dr. Kaku. This is Andrew Call here, and I just wanted to know if it was possible that we could have misinterpreted the results of the Michelson-Morley experiment. Let me know. Thanks. Bye.
Well, the short answer is no, but let me answer the question in more detail. In the 1900s, physics had this tremendous crisis. People were wondering that if light is a wave, then what is waving? That's a question that even children could ask. If light is a wave, then what is waving? And so scientists came up with this ethereal quantity called ether. Ether fills up the universe and is an absolute frame, so you know exactly where you are with respect to the stationary universe. So ether was this absolute frame of reference. Then we had the Michelson-Morley experiment, they shot light in two separate directions and calculated the relative speed differential if light goes in two different directions perpendicular to each other. And much to their shock, and the shock of the entire physics community, light traveled at the same velocity no matter which way it was going. Now, think about that for a moment. If you have a light beam and you shine a flashlight in the forward direction, or in the horizontal direction, vertical direction, or to the ground, you expect the speed of light to be different. If you're in a train, you expect the speed of light to be different if you shine a light in the forward direction. In fact, if the train is traveling near the speed of light, and you turn on a flashlight in the forward direction, you expect that flashlight to go twice the speed of light. Well, the answer was all of the above are wrong. This was a shock wave that no matter where you point the flashlight, light travels at the same speed, whether you're in a rocket ship, whether you're going north, south, east, west, diagonal, the universe didn't care. The speed of light was a constant no matter where you went. And therefore, it was Albert Einstein who finally figured it out. And that is that in order for light to travel at the same velocity in any direction, up, down, sideways, whatever, it meant that time itself has to be distorted. Time slows down the faster you move. And in fact, the GPS system depends upon that because we have to know what time it is in outer space. Duh. I mean, the astronauts can't go into outer space and not know what time it is. They have to know what time it is. But time moves at different rates throughout the universe. Time slows down for the astronauts. In fact, the astronauts are shifted in time by a few millionths of a second when they go up in outer space, a tiny, tiny amount. Also, time beats faster on the moon than on the Earth, all of which can be measured. Now, some people say, well, isn't relativity a theory? Therefore, it's not really proven, right? Wrong. Relativity is a law. It's not a theory at all. That's a problem with the English language. It is a law. Just like we have Newton's laws of motion, Einstein's laws are actually more powerful than Newton's laws of motion. And so the Michelson-Morley experiment showed that light travels the same no matter where you point the flashlight. And the only way to explain that incredible fact is to assume that time and space can change depending upon how fast you move. And we measure this. In fact, the Pentagon cannot fight wars unless the GPS system is calibrated to take into account relativity. And the space program will be thrown completely out of kilter unless we realize that the question, what time is it in outer space, depends on how fast you move, and it depends on where you are. As I said, time beats faster on the moon than it does on the Earth. Okay, let's take a short commercial break.
You're listening to Science Fantastic with Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, moving right along, let's take the next listener phone call.
Just wondering in what ways we are measuring the impact of the methane bomb in the Arctic. You know, are we monitoring those large stores of underground frozen methane? And, you know, what is the potential for that to be disastrous or lead to runaway climate change in this century? I wish you could provide us information on that because it's very hard to find information on that. Thank you.
Well, you ask a very important question, and that is, well, the Arctic is gradually thawing out. We know this for a fact. Even people who don't believe in climate change will acknowledge the fact that, yes, satellite data shows that the Arctic is warming up. For example, submarines that went underneath the ice caps in the 1950s, like the Nautilus, measured the thickness of the ice cap. We've since been there many times since then, and we find that the thickness of the Arctic ice sheet has gone down by 50%. Just in the last 50 years. I mean, think about that. In the last 50 years, we've lost 50% of the thickness of the ice sheet. In fact, in summer times, we now believe that the Arctic will be more or less ice-free in the coming decades. And the Russians are even depending upon this. The Russians have made very distinct claims that, yes, when the Arctic thaws out, they want to be there to claim part of it. In fact, I had a chance to lecture in Russia several years ago. I spoke in Siberia, of all places. I spoke in Krasnoyarsk in Siberia. And the people there say that, well, winters used to be brutal. I mean, really brutal in Siberia in the winter times. But hey, because of global warming, the Arctic is gradually thawing out, and they love it. Yes, some people actually love climate change, especially if you're ice-locked in Siberia. And when I went there in summertime, it was actually rather pleasant because of the fact that the Earth is heating up. And they also mentioned to me that because the Arctic is gradually thawing out, it means that mammoths and animals, prehistoric animals that died tens of thousands of years ago, are now coming out of the ice. So this is sort of like a Hollywood movie, The Revenge of Prehistoric Monsters. Because the Arctic ice is gradually thawing out, it means that we're beginning to pick up the carcasses of animals that died tens of thousands of years ago, like the woolly mammoth. Now, the question that was posed is about methane gas. Methane gas is a byproduct of the decay of organic materials. And if the Arctic ice is gradually melting, it means that, yes, the tundra is also melting. In fact, you don't have to go to Siberia, just go to Alaska, and you'll see the effect of the fact that the permafrost, the so-called permafrost that we consider to be frozen solid underground, parts of it are thawing out. And as the tundra begins to thaw out, it releases methane gas, and methane in turn is 20 times more potent than carbon dioxide in terms of causing climate change. So there's a potential of a runaway effect. Now, we should point out that this runaway effect is not going to happen anytime soon, so we don't want people to become hysterical and panic. However, it is something that has to be monitored very carefully by satellites and by climatologists in these various areas. The warmer it gets, that means more tundra is exposed. The more tundra is exposed, the more methane gas goes into the atmosphere. And the more methane gas goes into the atmosphere, it means that global warming accelerates because methane is much more potent as a climate change gas than carbon dioxide. And then the cycle repeats itself. So, again, there's no cause for immediate panic. In fact, the Russians, in some sense, are depending upon this so that they're not going to be so landlocked, and they're going to have access to warm water ports. And this is something that the czars of Russia wished for hundreds of years ago. And that's one reason why St. Petersburg, in fact, was created out of marshland by Ivan the Great in order to get access to warm water ports and trade with the West. And so then the questioner asked another question. How dangerous is this? Well, it is potentially very dangerous because we're messing around with the atmosphere of the planet Earth. However, it's not a problem that's going to peak in this generation, but it's a problem that our children and our grandchildren are definitely going to have to face. And again, you don't even have to believe that human activity is generating climate change. We know that the climate change process, whatever caused it, is in effect. And it could reach a point where it becomes autocatalytic. That is, it feeds on itself, and you get a chain reaction. We're not there yet, but again, the Russians seem to welcome this possibility. Most of us fear this possibility. Okay, well, let's take the next listener phone call.
Why do you call the string theory a theory if it cannot physically be proven?
Well, you ask a very embarrassing question, but a very fair question, and that is that sometimes great theories are proposed, but a test, a knockout test of the theory could take decades. And that's the way it is with all sciences. For example, when the theory of continental drift came out, it was laughed at for decades. In fact, I remember as a kid in elementary school, it was pointed out that, gee, doesn't Africa look like Latin America if you put the two continents together? The elementary school teacher actually laughed and said, ha, that's just a theory that's obviously incorrect. How can a continent move? I mean, continents are huge objects. How can you move a continent? But the elementary school teacher was fair and said that, yes, it is a theory. It's a theory that cannot be proven and probably is incorrect. Well, now we know that that is, of course, the guiding principle behind all of geology. Just like evolution is the unifying principle of all life and DNA on the Earth, continental drift is the unifying principle of all geology. But it took decades to actually prove it. In fact, it wasn't until we had submarines that could go down to the bottom of the Atlantic Ocean and photograph new volcanic materials coming out of a crack in the Atlantic Ocean that it was finally, quote, proven that we can actually see continents move. Continents move at the rate at which your fingernails grow, about an inch every few months, and we know that it's true.
You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, in this hour, we're throwing the lines open because this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Hi, this is Brady calling from Denton, Texas. I'm a big fan. I'm kind of a today for the moment and hoping to change that. And I was kind of curious as to, and if you could possibly give an explanation, how scientists are able to entangle particles in the lab and how this process occurs without scientists, like in nature and the universe. Thank you.
Okay, well, you ask a question that is at the cutting edge of computer research, and one day your computer may depend upon this concept called entanglement. Well, first of all, we have a theory of atomic physics. It's called quantum mechanics. We see no deviation whatsoever from the laws of quantum mechanics, and it's what I do for a living. And in quantum mechanics, all matter is a wave. All matter has wave-like properties. And when you have two electrons that are very close together, in fact, touching each other, they vibrate in unison. They go up and down, up and down. They vibrate in unison. Now, separate them. When you separate these two electrons, then there is an umbilical cord. An umbilical cord you cannot see, which mysteriously connects one with the other. Einstein hated this. Einstein himself did not really believe in quantum mechanics, but hey, what can I say? He was wrong on this question. And this entanglement, therefore, means that if you jiggle one electron, then there is this mysterious umbilical cord connecting it to its twin, and it understands the fact that its partner has been jiggled. This experiment has been done. It was first proposed in 1935 by Einstein himself. In fact, Einstein created this experiment, this mind experiment, in order to disprove quantum mechanics. He said that any vibration of one electron would immediately spread to the other electron by this umbilical cord, and it would travel faster than the speed of light, and bingo. Says nothing can go faster than the speed of light. Quantum mechanics is wrong. So Einstein thought he had it. Einstein thought that he had the fatal plunger that would then kill off quantum mechanics. Well, this experiment has been done. We do it every day in our physics laboratories. And what can I say? Einstein was wrong. There really is this umbilical cord. It's called spooky action at a distance. These are Einstein's words. And he invented these words, of course, to try to smash it. But instead, hey, Mother Nature is what Mother Nature is. And it turns out that Einstein was wrong. Then the next question is, can you use this, as many science fiction writers have proposed, to send a message faster than the speed of light? if this information travels instantly, then does it violate relativity? We'll answer that after the break.
This is Science Fantastic. Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. We're throwing the lines open because this hour is your hour. Okay, well, let's get right back and take the next listener phone call.
Hi, Dr. Michio Kaku. This is Aiden Cumming-Teicher, and my question is, what number one advice would you give to a young entrepreneur who wants to become a quantum physicist? Thank you.
Wow. Well, that's a tough question, but I think your question is in two parts. First of all, to become a quantum physicist, and second of all, to become an entrepreneur. So let's try to break this down. First of all, if you want to become a quantum physicist, I would, first of all, advise you to read a lot of the science books out there. When I was a kid, there were almost no science books at all about the quantum theory, but now there are quite a few good ones, including my own. And so read up. Listen, watch the science shows on the Discovery Channel, on History Channel, National Geographic. A lot of good shows about the astronomy, about the universe, about Einstein's theories, all of it animated on television. So the first thing is keep up with popular science by reading magazine articles, by reading books, and by watching the TV. But, hey, you can only go so far reading popular books. You have to settle down and learn it. And that means that in college, I would start to take mathematics and physics courses. Now, one question that I sometimes get is, do you have to be a genius in math to become a physicist? And the answer is no. However, you do have to be competent. That is, you have to master calculus. First year calculus, of course, is essential. Second year calculus, if you can hack it. But you have to pay your dues. And once you graduate, then there are a variety of jobs that you can apply for. And I'll summarize some of them after the break.
Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a quick question about how to become an entrepreneur as a quantum physicist. Well, first of all, there are many steps involved. And go to my website. I have an article entitled, So You Want to Become a Physicist. In fact, I remember when I was in elementary school, in fact, when I was in 5th grade, we had these pamphlets about what you want to become when you grow up. And one of the pamphlets had a very intriguing title, and that is, What do physicists and baseball players have in common? And I thought, ooh, gee, this sounds interesting. So I picked up the brochure, What do baseball players and physicists have in common? And I found out that they both get paid to do what they love. Baseball players get paid a lot of money to do what they love. Physicists, well, we don't get paid as much, but we do get paid to do what we love, which is quantum physics. And that's the link. And I thought to myself, hey, how can you beat that? How can you beat that? Getting paid to do what you love. And so like I said before, A, start to read about science, watch science programs. B, in college, well, take physics courses, but you have to take math. Not advanced calculus so much, but at least you have to have about a year's worth of calculus. And then once you graduate, there are three possibilities. One possibility is to work for the government. You can work for the National Bureau of Standards, which has a new name now, or you can work in private industry. That's where the money is. I mean, after all, Hewlett-Packard, the Varian brothers, many of the biggest names in high tech came out first as physics and electrical engineering majors and then went into business. And third, you can go into academia, which is what I did, because then if you're tenured, you can pretty much do whatever you want and get paid to do it. What's there not to love about that? Now, if you want to become an entrepreneur, there's a whole nother dynamic involved. First of all, you have to be content to, well, fail. Failure is one of the byproducts of being an entrepreneur. You're not going to make it big on the first try. Nobody ever does. But you have to have money to back your ideas. Hewlett-Packard, for example, they went door to door in suburban Palo Alto, where I grew up, asking for people to invest in their garage electronics factory. That's right. They had a little electronics factory in their garage, and they went door to door asking people to invest. That's how Steve Jobs did it. That's how Apple Computers got started. That's what the Varian brothers did in their garage. They would go door to door trying to line up investors. Now, today, of course, if you're sitting on a hot piece of software or hardware, you don't necessarily have to go door to door and advertise your garage equipment. However, that's one way to do it. Okay, well, let's take the next listener phone call.
My question is, why does observation collapse quantum wave function?
Well, you ask a question which goes to the very heart of quantum mechanics, and that is, if matter is a wave and it vibrates, and these vibrations talk about different possibilities, then how does the wave collapse to give you reality? Reality doesn't look wave-like. We don't see the fuzziness and the waveness when we actually look at the electron. We know the electron is here, right there at that exact moment. And so the wave function had to collapse. And this has been a source of consternation and debate for the last 80 years. For 80 years, the giants of physics, Einstein, Niels Bohr, Schrödinger, debated what does it mean when the transition is made between the wave-like properties of the subatomic world, which we can measure, and the fact that, well, electrons do seem to be like little steel balls. Where is the wave-like property? Well, if you look at a quantum mechanics textbook, it simply says, as you pointed out, that the wave collapses. Now, people didn't like that. For 80 years, people didn't like that. But what can you do? Quantum mechanics is a cookbook. It's a recipe book. It gives you the right answer every time you scatter electrons, protons, pi mesons, Higgs boson. Every time you scatter subatomic particles off each other, quantum mechanics comes out exactly right. Well, there are several ways of resolving this paradox. I'll tell you my way. One way is that, well, these waves represent different universes. And therefore, when you make a measurement, the universe decides to be in this universe versus another. In other words, there is a fork in the road. And before you hit the fork in the road, you can be in all different possible states, but after you make a measurement, you are in one state and not in a wave-like state. This is the many worlds theory. It's very controversial, but hey, most of my friends, many of the Nobel laureates, believe in the many worlds theory, which says that there are an infinite number of parallel universes. That when you make a decision, the universe splits into an infinite number of possible universes. So in one universe, you're listening to my radio show. In another universe, you decided to go out and get a hamburger, and you're not listening to my radio show. In another universe, you married somebody else. In another radio show, you went to a different college, chose a different career. Can you rule this out? And the answer is no, because electrons make a decision the same way that you make a decision. And again, this is a philosophical debate that's been raging for 80 years, and we're not going to be able to resolve it in the next 5 seconds, but get a copy of my book, Parallel Worlds, and in that book we go through the ins and outs of one of the greatest questions in quantum mechanics, and that is, can an electron be two places at the same time? Are there multiple universes? Find out.
You're listening to Science Fantastic with Professor Michio Kaku. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we throw the lines open because this hour is your hour. Okay, well, without further ado, let's jump right in because it's open mic on Science Fantastic. Let's take the first listener phone call.
Okay, so I have a question that I've kind of had for a little while now, and everybody I've tried to ask hasn't been able to answer it. And I've been a big fan of yours for a long time, and I've often thought that it would take somebody like you to answer this question. So I figured I'd ask you. So with the sound barrier, it's the compression of the sound waves, as I understand it, that causes that resistance. And once you break through that, you break the sound barrier, sound boom, etc. Well, with the speed limit of light, is that caused because of a light barrier? Is it a compression of light or something similar to that? Or maybe time is related to it in a sense? And if you were to break that light barrier, would you go back in time, or what do you theorize would happen? Thank you. Bye.
Well, the answers to your questions were all worked out in 1905 by a young physicist who was 26 years old by the name of Albert Einstein. He couldn't get a job being a physicist, but he worked out the theory of relativity, which answers all your questions. First of all, you're right that the sonic boom in an airplane or jet takes place as you approach the speed of sound. All the sound waves begin to compress in front of you, and as you hit the speed of sound, you break through the compression of all the waves that have then squeezed in front of you, and that creates the sonic boom when you break the sound barrier. Now, scientists used to think that perhaps that's the way it worked with light, that light also has a sound barrier of sorts, and as you break through the sound barrier, well, maybe you can't, and that puts an upper limit to the speed of light. Well, we now know that all those theories are, in some sense, wrong. Just before Einstein proposed relativity in 1905, there were a lot of schemes like what you just proposed. People thought that the ether, that is, the substance that fills up the vacuum, was sort of like a fluid. And yes, you would have sonic waves in this fluid, and yes, you would have all these bizarre properties as you approach the speed of light, and therefore, experiments were done to measure this effect, and they found none whatsoever. You know that if an airplane moves toward you, away from you, at an angle, that the airplane seems to travel at a different velocity. But light is different. If a flashlight points toward you, a flashlight points away from you, or you throw the flashlight into outer space near the speed of light, the speed of light of the flashlight is the same. The same no matter where you point the light beam, light always travels at the same velocity. How can that be? It was Einstein who finally figured it out. It's not the compression of a substance that causes all these bizarre properties. It's not the electromechanical stretching or compression of an ether that explains the Michelson-Morley experiment. It's that space and time itself can be altered, compressed, that the faster you move, the slower you get, and the more compression takes place. Space itself is compressed as you move in the forward direction and as you approach the speed of light. That's just the way it is, independent of the properties of the ether. According to Einstein, ether may or may not exist, that is a substance of the vacuum, but it is irrelevant. It's not measurable. It has no measurable effects. Now, sometimes people say, well, how can that be? That violates common sense. If you throw a flashlight toward you, against you, you shine a flashlight at an angle, the velocity of light should change. Nope, it doesn't change at all. That violates common sense. But hey, the universe doesn't care about your common sense. That's just the way the universe is. We measure it every day with your GPS system. Every day your cell phone depends upon all these bizarre distortions of space and time. Get used to it. That's just the way it is. Einstein comes out on top for the last 100 years. Okay, let's take the next listener phone call.
Yes, my question is in regards to the colonization of Mars. I was wondering on your thoughts on the use of mushrooms on Mars due to their positive reaction to radiation, and seeing as how there's so much radiation on Mars. Thank you so much. Bye.
Well, if you saw the movie The Martian, you realize how difficult it is to grow anything on the planet Mars. First of all, the atmosphere of Mars is very cold. Most of the time, the planet itself is frozen solid, so you can't grow anything in the soil because you hit permafrost almost immediately. The atmosphere is made out of carbon dioxide, which is good for plants. Plants love carbon dioxide, but it's extremely cold, and there's no soil. There's no soil to speak of, because where does soil come from? Soil comes from the decay of previous generations of plants. But you see, there are no previous generations of plants on Mars, and so it's difficult to raise plants on the surface of Mars, which is frozen solid. Now, you mentioned mushrooms. Mushrooms, in fact, will grow in damp environments, but not if it's frozen solid. So the first thing you have to do is somehow unfreeze the surface of Mars. And that requires you to change the atmosphere of Mars or to have other schemes to inject heat into Mars. One suggestion is to have gigantic solar panels in outer space orbiting Mars, shining and concentrating sunlight from the sun down to the surface of Mars, heating up the surface. So in other words, use solar collectors in outer space orbiting Mars to focus sunlight on the surface of Mars. Elon Musk, the billionaire behind Tesla Motors and SpaceX, he advocates using hydrogen warheads, hydrogen bombs, to perhaps begin the process of melting the polar ice caps, which are made out of solid carbon dioxide and solid water. So yet another mechanism is to inject methane gas. Methane gas is a greenhouse gas. It is 20 times more volatile than carbon dioxide in terms of capturing sunlight. And so methane gas has been proposed as one way to accelerate a greenhouse effect on Mars. So in other words, it's all great, these ideas about putting plants on Mars, but first you got to thaw out the frozen permafrost and get some soil before you can plant anything on Mars.
Yes, Professor Kaku can help you with your homework. He can even help you with your kids' homework. But only if you ask. This is Science Fantastic. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. Okay, well, let's move right along. Let's take the next listener phone call.
Given what we are doing to our home planet, do you think we have reached a level of intelligence where we should colonize other planets? Or should we wait until our species maturity level matches our own intelligence?
Well, you ask a pretty heavy question, but let me say this. The main limitation to colonizing the planets is really not a question of our maturity, because, of course, our civilization is quite primitive and quite young when compared to an advanced civilization. The real problem is, well, cost and the mechanics of the colonization process. I mean, let's be fair about this. We're not going to be able to colonize the planets for centuries. That is, in this century, in the 21st century, we'll just begin to have the first outposts, perhaps on Mars. Perhaps a permanent colony on Mars by the end of this century, but not booming cities, not gigantic civilizations on Mars. No, just a few outposts on the red planet. Now, in the next century, once we have robots that can do a lot of the heavy lifting, that can perhaps even self-generate and create self-generating robots, at that point, perhaps the first cities may begin to be formed on the red planet. But to create a real civilization on the red planet will take, on the scale of centuries, because of cost, because of the enormous distances and hazards involved. Now, you ask a very probing question. Are we really mature enough to handle this? And, well, as Einstein once said, our technology has outraced our humanity in the sense that we have all the ways in which we can split the atom, we can sequence the gene, we can begin to manipulate life itself. But hey, we can't even figure out simple things like immigration or income inequality on the planet Earth. So, in other words, we have a long ways to go before we become mature. But when could we become mature? Well, as a scientist, we believe that energy is the way to measure the progress of a civilization, at least the gross way in which to measure a civilization's progress. And we are on this scale a type 0 civilization. We get our energy from dead plants, oil and coal. But by the year 2100, we should become a type 1 civilization. That is a civilization that harnesses truly planetary power. We're talking about the creation of a planetary civilization, a civilization that is multicultural, that is scientific, that enjoys freedom, a civilization that is planetary. That's called a Type 1 civilization. Type 2 civilization is like Star Trek. It is stellar. It actually controls the energy output of an entire star, like the Federation of Planets on Star Trek. So Star Trek would be a typical Type 2 civilization. And then a Type 3 civilization is galactic, like Star Wars. The Empire would be a typical Type 3 civilization. So you see, on this scale, we're a long ways from being able to colonize a planet because we're still basically a Type 0 civilization. But the most dangerous transition is between Type 0 and Type 1. A Type 0 civilization still has all the savagery, all the sectarianness that typifies its rise from the swamp. And however, by the time we become Type 1, we have a shot at maturity, a shot at creating a truly planetary civilization. Okay, well, moving right along, let's take the next listener phone call.
Hello, I was wondering why time is considered a dimension. I understand that we have 3 spatial dimensions, X, Y, and Z, and we can access those dimensions at any time. But time seems to be a weird dimension because we're forever stuck in this present, and I want to know why that is considered a dimension, why it's considered our 4th dimension. Thank you.
Well, your question would require a book to answer, but we'll take a crack at it after the commercial break.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question that is pretty much impossible to answer during the duration of a radio program. However, let me give you some basics about time. First of all, we say that time is the 4th dimension. Now, what does that mean? That means it takes 4 numbers to typify any event. So if you want to meet, let's say, somebody for lunch in Manhattan, you would say, meet me at 12 o'clock at the intersection of 42nd Street and 5th Avenue on the 10th floor. So it takes 4 numbers, 3 numbers to specify space, 1 number to specify time, and any event can be categorized, therefore, by 4 numbers. So that's why we say that space is 4-dimensional. But that said, time is different from the other dimensions. You can freely go in space. In the X direction, you can go forward or backward, left or right. However, time is different. Time, you can go forward, but going backwards is very difficult. You would have to do all sorts of, create all sorts of havoc with space and time in order to go backwards. And mathematically, we say that that's because space-time is elliptic. That's the mathematical way of expressing it. And using the mathematics, we get bingo. Every time we get it right once we use Einstein's theory of space and time. Now, then the next question is, why? Why is it that time is different from the other 3 dimensions? That is, it takes 4 dimensions to typify any event in the universe, But while space, you can go back and forth easily in space, you cannot easily go back and forth in time. And, well, the short answer for that is we don't really know. Now, the highest theory of space and time that we have, that even includes Einstein's theory as a subset, is string theory. But even in string theory, we simply put in the nature of space and time. In string theory, instead of having 4 dimensions, we have 11 dimensions. That's right. We think that the original Big Bang took place in 11 dimensions. So when people say if the universe is expanding, what is it expanding into? It is expanding into not 4, but 11-dimensional hyperspace. But even in these 11 dimensions, time is still special. And why is that? Well, it turns out the string theory is not mathematically consistent unless you have at least one of the dimensions become elliptic. And so, well, that's not really answering the question in words that can be expressed in English. But mathematically speaking, string theory itself is inconsistent. Inconsistent unless time is different from the other dimensions. By the way, if you want to see the mathematics behind this, get a copy of my book, Introduction to Superstrings and M-Theory, and you can see the mathematics behind everything I just said. Okay, well, moving right along, let's take the next listener phone call.
Yes, I would like to know if there's such thing as the future, as if the future is a movie that's already been pre-recorded that we just don't know yet, or if the future is a probability spectrum where anything can happen and there is no specific future that is going to happen, whether we know it or not. Could you make that distinguishment and explain that, please?
Okay, I think you're getting the inspiration for your question from the movie The Matrix. The movie The Matrix stimulated a lot of philosophical discussion, even among scientists, about the question, well, is the universe a simulation? We know what a simulation is. To simply take a videotape, put it in your computer or your DVD, and bingo, all of a sudden you have people dancing and laughing and acting as if they were living in a real universe. But we know, of course, that it's nothing but a simulation. It's called a video. And then the next question is, are we living in a video? And if we are, could we ever know it? Can we create an experiment that'll determine whether or not everything you see around you is an illusion, whether it's been uploaded into your brain? Now, you know the movie The Matrix. In the movie The Matrix, reality as we see it, as we visualize it, is actually a computer program, a videotape. And we think we have free will in that videotape, but this universe of ours was created by aliens that conquered Earthlings and have reduced Earthlings to batteries. That's our function, to create electrical energy for the machines. Now, here's the question. Do you know, can you create an experiment that'll prove or disprove whether or not you're in a simulation? My personal point of view is no. Maybe you are. Maybe reality is all an illusion. Maybe you're in a dream and you'll wonder when you're going to wake up from that dream. Well, how can you make an experiment that'll tell the difference? Personally, I think that is, quote, beyond science. And after the break, I'll add a few more words to that. The question is, can you prove things like, is the universe a simulation, or what about reincarnation? All these questions, we're going to say a few words after the break.
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour. Well, before the break, we had a question that is actually rather difficult to answer, and that is the universe a simulation of some sort? And again, if you're a fan of the movie The Matrix, you know how difficult it is to tell the difference between a simulation that is uploaded into your brain and reality itself. Now, science is based on things that are testable, falsifiable, and reproducible. That is the essence of what science is. However, there are things that are not testable, not reproducible, and not falsifiable. That doesn't mean it's wrong. It just means that it doesn't fit with our usual conception of science. For example, reincarnation. Sometimes at a cocktail party, you may meet somebody who swears that they are the reincarnation of Cleopatra. And you give some simple questions to test their knowledge, and of course they get all the answers wrong. But then they say, well, you see, the history books are wrong. How do you know the history books are wrong? Because I am Cleopatra. I lived through it. I know the history books are wrong. At that point, well, end of discussion. There's no progress you can make because you cannot falsify that statement. If someone claims to be Julius Caesar, well, how do you falsify that statement? Because if they get all the facts wrong, the person says, well, I am Julius Caesar. That's why I know the facts are wrong. In the same way, you cannot create a test that'll test whether or not reality is a simulation or not. Maybe it is. Maybe it isn't. Now, the questioner also asked a question about quantum mechanics. Is the future determined, like in a videotape, or is the future probabilistic? That is, many possible futures that can exist. Well, if the universe is a simple videotape, then the answer can be made, and the answer is it is not possible. That's because we have quantum mechanics. Quantum mechanics says the universe is not determinable. That is, there's always a probability that the universe could go in a different direction. And we see no deviation from quantum mechanics at all. So the short answer is the world a videotape? And the answer to that is no, because the videotape is deterministic. Quantum mechanics is not. But can that whole thing be a simulation? Well, the short answer is I don't know.
Does he know about string theory? He wrote the book on it.
You're listening to Science Fantastic. Here's
everyone's favorite physics professor,
Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, it's open mic on Science Fantastic. Okay, well, moving right along, let's take the next listener phone call.
I was just listening to the professor on the radio. He was talking about the expansion of the universe and comparing it to the surface of a balloon, and that there was no center spot that we know about for the origin of the Big Bang. And reading about astronomy, I was reading about Professor Edwin Hubble and redshift, and how he pointed his telescope toward the other expanse of the universe, and he noticed that the universe is not only expanding, but it's expanding at an ever-increasing rate. My question is, what direction did he point his telescope, and if the universe is on the surface of a balloon, how does it have any depth in order that he can determine that it's expanding?
Yes, well, you ask a question because many people are often confused by the discovery of Edwin Hubble. Back in the 1920s, it was so simple when you talked about the universe to an astronomer. The universe was the Milky Way galaxy. End of story. Period. The universe was the Milky Way galaxy. And the Milky Way galaxy itself was maybe 100,000 light years across. But then, as you pointed out, here comes Edwin Hubble that finds that there are other galaxies out there. That our galaxy is just one among billions of other galaxies, and then he calculated the speed at which these galaxies are moving, and he found that they were moving away from us. No matter where you pointed your telescope, in any direction you point your telescope, all the galaxies are moving away from the Earth. So either the Earth is the center of the universe, which we don't believe, or the universe itself is expanding. So again, use the analogy of a balloon. If you're on the surface of the balloon, then an ant would see all the other points of the balloon moving away from it. So if you were to paint stars on the surface of a balloon and put an ant on the balloon, the ant would see all the dots moving away from it. But then if you were to ask the ant, where did it all come from? From what point did the expansion take place? At that point, the ant would say, the question makes no sense. I can only see what's on the surface of the balloon. That's it, period. There's nothing else but the surface of the balloon. Therefore, to the ant, the center of the balloon makes no sense. the center of the balloon is beyond the comprehension of the ant. Well, in the same way, where did the center of the expansion take place? Was it to the left, to the right, up, down? No. You cannot point to a direction in the universe and say that's where the Big Bang took place. Now, there are two ways you can look at this. You can either say that once upon a time the universe was very tiny, even space itself was very tiny, like a little ball, and it exploded in all directions as a consequence. Therefore, in some sense, where did the Big Bang take place? All around us, because the universe itself was tiny. The universe itself was very small at the beginning of time. And so where did the universe expand from? Everywhere. Because if you're an ant sitting on a tiny, tiny ball, and you ask, where is the center of that tiny ball? The ant would say, everywhere. But now the universe is expanding in a very large way. And another way to look at it is to say that the universe is expanding in another dimension. At that point, the ant says, I give up. I don't understand this other dimension because my eyes can only see in two dimensions. Well, that's where Einstein comes in, because Einstein says that perhaps there's a fourth dimension, and the universe is expanding into hyperspace, into a dimension that we ants cannot visualize.
I want to talk with you about evolution. It's actually a board game. Yes, it's a new board game you can play with your family, and it's called Evolution, the Beginning. A few months ago, I played for the first time. I must say I was a little bit hesitant at first. I wanted to make sure the game was not complicated. Dear old Dad must be able to play this game with the kids at Christmas. So I learned about the goal of the game, and it turns out to be very simple. Eat as much food as possible. Now, to eat the food, each player takes turns creating and evolving their own species. Evolution in the Beginning is based on science. Your species must adapt and change in order to be competitive. Just like in life, the goal of evolution is to be the fittest. There are hundreds of ways to evolve your species, and the fun part is, it's up to you. Evolution in the Beginning is available now, only at Target stores. Just look for the big dinosaur on the box. In the game section, it's science without feeling like science, and that's the fun. You'll find it all at Target stores. Evolution, the Beginning.
Okay, well, moving right along, let's move on to the next phone call.
Hi, Dr. Kaku. My name is Emmanuel. I wanted to ask you, what do you think of Tesla's theories of transmitting power through the air?
Well, you ask a very interesting question because Nikola Tesla, of course, was one of the great pioneers of the electronic age. It's a very sad story. Many of his patents were more or less stolen from him. He never got the financial rewards that he deserved because he was sitting on a ton of extremely valuable patents, and he did not have a fleet of lawyers to protect them. And so pretty much the electronics industry got off the ground without him. Now, Tesla had some great ideas, but he also had some strange ideas as well. He was trying to basically communicate with Martians. He thought that you could create ray guns, which we think we can create, but with laser beams, which was beyond his technology. And he thought you could shoot electrical energy through space. It turns out you can through what is called induction, but it's very inefficient. You can perhaps, for example, recharge your cell phone battery from a distance, but it's very inefficient. And it may not be too helpful either, because, of course, you are shooting electromagnetic radiation through the air in large quantities. But in this sense, Tesla got it right that, yes, you can, in fact, use what is called induction to shoot electromagnetic energy through the air. And that's how some people actually charge up their cell phones, by putting the cell phone next to this recharger without any wires at all. Okay, well, that's it for Science Fantastic. Good day.
You're listening to Science Fantastic.